Hello everyone, today we are going to represent a paper named Characterizing Equivalent Electrical Circuit Model of Lithium-ion Battery with GWO Optimizer. This is our teammate and speakers. This is our outline. We will start by introduction and we will introduce battery modeling. Next, we will show what main problem the paper discovered and how they use GWO algorithms to solve this problem. Fourth one is simulation analysis. We will show their experiment results. And the last one is conclusion. Okay, let's start at introduction. Because of growing awareness of environmental sustainability and reduced carbon emissions, electric vehicles have become a choice. The advancement of EVs, which means electric vehicles, has subsequently catalyzed the exploration and research into battery technology. The lithium-ion battery has become one of the important parts of EVs, since it is responsible for powering the motor and enable the basic but key functionality of cars. Electric vehicles are all about speed and range, and lithium-ion batteries are the perfect field to make that happen. Instead of that, lithium-ion battery has many advantages, such as no memory effect, low self-discharging rate, high power density, and minimal memory effect. However, charging temperature and battery aging can significantly impact the safety and durability of electric vehicles. And to predict a battery's health, SOH, and remaining charge, SOC, and dynamic voltage response, we leverage two powerful techniques. And in first sentence, SOH represents state of health, and SOC represents state of charge. And leveling modeling approach is grounded in time domain characteristics, whereas the AC impedance modeling method is based on the electrochemical attributes within the frequency domain. Researchers use a second-order RC circuit and an EHPPC to determine how a battery voltage changes over time domain. And the EHPPC represents extended hybrid pulse power characterization. And then, through a rich set of experiments, the corresponding dynamic voltage waveform can be obtained. They then employ the GWO optimizer to fine-tune the EEC model's R and C parameters, resulting in the most accurate result. The accuracy is measured by how closely the model prediction matches the actual battery behavior using root mean squared error.
The second part, equivalent electrical circuit for battery modeling. As shown in Figure 1, a second-order RC equivalent electrical circuit was used to characterize battery dynamic performance. There were 5 circuit parameters like R0, R1, and R2, and C1 and C2. And there is one dependent voltage source representing open circuit voltage in terms of different SOCs. And for the voltage response, the voltage response of 2RC based on EEC model. EEC is the equivalent electronic circuit and was derived as the equation 1. And for the 8 RC pair, the current and voltage relation was formulated as the equation 2. And then we can use the differential equation was solved to induce the voltage response function as the equation 3. Likewise, the voltage response function for the R2 and the C2 pair was obtained as the equation 4. As for the voltage drop on R0, equation 5 was used. In this way, the terminal voltage was derived by substituting equation 3 to 5 into the equation 1. Considering the reaction period in the EHPPC, voltage response was formulated in equations 6 and 7. And in the 6 and 7, where the V of T star indicate to initial voltage value at the reaction time. Since I equals 0, voltage drop equals 0. The complete voltage response under any circumstance that can be simulated with equations. Moreover, in order to construct an EEC model, a series of virtual tests needed to be conducted to equivalent the battery cell. This test encompassed the capacitor test, OCV SOC test, and dynamic voltage response test. And the capacitor test. The capacitor test is instrumental in establishing the discharging capacitor under different temperature conditions. This is thus the second factor of conclusion, the state of charge SOC, using the Coulomb-Counting method, was outlined in equation 8, where the T represents each time step, I is the discharging current, and Q is the available capacity obtained from the capacitor test. And the second, OCV SOC test. To derive the relation of OCV and SOC can obtain the OCV curve. A discharging current of 3/1C was employing the discharge cell starting from a state of charge at 100%. Down to the observation point, it was possible for 5 hours to record the opening circuit voltage. The open circuit voltage was measured at intervals of 2% between the SOC level, ranging from 100% to 90%, and from 10 to 0, while the SOC levels were measured at 5% intervals.
Okay, so in this chapter, I'm going to talk about the main problem. In the last chapter, we have introduced the electric circuit model, and now we want to know the R0 to C2, these 5 parameters we need to be characterized. So to evaluate the simulated and the actual voltage, we include the root mean square error to evaluate this correctly. So like in this formula, Y1 is the measured voltage and white hat line is the simulated voltage. And in my opinion, I think that we use square to ignore the sign between the negative and positive value, and we use the root sign to normalize our error. Yes, this is my Okay, so the next we're going to talk about GWO algorithm. In GWO algorithm is a wolf hunting behavior and is a hierarchical social structure is observed. And actually we ranking the top 3 optimal solution as alpha, beta, and delta. And omega wolf is the consider the position to locate the prey. And in next chapter we need to characterize 5 parameters, and so we convert it into a vector form, so we can easily use the GWO algorithm. And I is the wolf index. Okay, so next we're going to talk about the 3 main stages of GWO algorithm: encircling, hunting, and attacking.
Let's talk about the encircling stage. In this stage, the wolf collaborates to surround and converge toward the prey's location, and identified by the alpha, beta, and delta wolf. This phase is pivotal in refining and improving the solution, further setting the stage for subsequent hunting endeavor. And in the following formula, D represents the distance between the wolf and its prey, and XP represents the location of the prey. And C and A are vector coefficients defined by the following formula under which our R2 is the uniform distribution in 0 to 1, and A is the linear decrease from 2 to 0. T is the iteration number, and T max is the maximum iteration number. And next, we are going to talk about the hunting phase. Once the potential optimal solution is identified in the encircling phase, the wolves shift their focus toward converging upon it for further exploration. Led by the alpha wolf, the pack refines their position in response to the prey's location, continuously striving to maximize the fitness of the solution. And here's the following formula. X alpha beta gamma is the position of the alpha beta gamma wolf, and X is the position of the search engine, which need to be represented in the position, the total position of the alpha beta gamma wolf, and and D is the distance between the searching engines and the wolf, which is alpha beta gamma. And last, we are going to talk about the attacking and the searching phase. And during the attacking phase, when the potential optimal solution starts moving, the volume of A gradually decrease and make the capital A fluctuation in minus A to A. And if the capital A is lower than 1, the wolf will try to approach the solution, which is the prey. And if the capital bigger than 1, the wolf will move away from the solution and try to search other solutions. Then, in the searching phase, apart from relying on the capital A to dictate the gray wolf actions, capital C that can randomly modify the significance of prey. Influences the gray wolf attraction to potential targets. Similar as the attacking phase. If the capital A is bigger than 1, the prey will be more attractive to the wolf. Otherwise, if it's lower than 1, the wolf will have lower interest about the prey. And this ensures that the gray wolf doesn't overly fixate on nearby prey, which is the local minimum, and thus preventing the chance to pursue superior targets, which is the global minimum. Okay.
So on this page, I'm going to say again the whole workflow of GWO algorithm. First, we will initialize all location and temperature. And the most important part, we're going to evaluate the best RNSE value in our simulation and actual voltage. Based on this, we can order our top 3 value of alpha, beta, and delta wolf. And based on this, we can update our each location of the pyramid each wolf or each location of wolf, and use our equation by update formula of equation 9 to 15, which is in the page of this formula, and then until we reach the optimal value or the interpolation setting, yes.
To say vector simulation exercise. In this study, a battery cell monies INR 21700 P4 2 bits. It is a battery cell. The type of cavity is 4,200. Okay. The normal voltage is 3.7 voltage. Charge voltage is 4.2 voltage. Discharge voltage is 2.5. Next charge current is 8.4. This picture shows the measured result of OCD and SOC for the cell, which is realized dependent voltage source in VOC in EEC model. This case shows the charge voltage is 4.2. And then verifying the equivalent curve model performance, EHPPC was constructed. We use struct screens constant for over 30 seconds of discharging pulse. This is the first time discharging pulse. Then we follow stop 600 second pulse. The second is the pulse. Then suspend screen 30 seconds of charge pulse. This is charging pulse the first time. Then again following by 600-second pulse. These screens were implemented at the 6 decision per negative, 6 times. Especially 20% and 33%, 50%, 1 times, 2 times, and 3 times. This is 20% charge. This 2 times is 33%. Apply at each SOC observation point. This is GWO implement determination the proposed current parameter after with high precision. This is the GWO precision layer. And use this parameter to do the simulation. The simulation and the experiment results are presented in this figure. And their difference in these 2 figures mainly differ from the time shift of the voltage represent response due to the X-system relation times. The convergence history of the search persists. It shows in the next picture, where RMSE is greatly reduced as the iteration. Definitely, GWO convergence is to optimize result where RMSE was 0.0021 and the maximum voltage error was 0.15. This shows the RES is reduced 0.0021, and there it shows the voltage error is 0.15 voltage. And the conclusions. We pose the system approach to find out the circuit parameter for the battery EEC model. Based on the 2RC EEC model, the current and the voltage relation was deferred to simulation the dynamic voltage response. Then the EHPDC test was designed and carried out on the display cell to obtain actual battery voltage response data. In addition, capacity test and OCD SOC test were concluded to obtain the discharge capability and the OCD SOC relationship of the GWO is equivalent to search for the current meters of the 2RC EEC model. Eventually, the proposed 2RC EEC model was simulated for the parameters of the battery cell, where the simulation voltage with active RMSE as low as 0.0021 and the maximum voltage difference down to 0.15%. Our presentation is over. Thank you.
Thanks for the nice presentation. I would like to have a few questions. Could you answer what's the parameter you're gonna decide in this using GWO? What parameter? Or what variable?
So in this paper, we're going to decide the 5 parameter is R0, R1, C1, R2, and C2, which represent the second order RC circuit model in this stage.
Yes.
These 5 parameters is really going to recognize.
Yes, very good. And what's the objective of this research?
So the objective of the research is going to reduce the error between the simulated voltage and the actual voltage in the circuit model. So we can see that the root mean square error in this. We're going to minimize this root mean square error.
Yes, very good. Here are the 2 very key points of the research. Those are what variable you're gonna decide and what's the target. And could you move on to a simulation analysis and show the EHPPC curve? Yes, I have a question about this experiment. This experiment I know is called EHPPC. So, do you take the major current or major voltage as the experimental result to take this value into the evaluation of RMSE? Current or voltage? Current. And so your answer is
No, I think we use measure current to integrate the current and get the whole state of charge. And we measure out the voltage to minimize actual voltage and output voltage. So I think the state current is because we need to measure the state of charge. State of charge is this. And actually, we test our voltages. The root mean square error is needed.
yes. I agree with you that you take the voltage response of EHPPC, take this data into the RMSE calculation. Yes, that's correct. I want to emphasize that in this test, we set the pulse, like discharging pulse and relation time, charging pulse, relation time, in order to have the voltage response. And this voltage response is taken as the correct answer, because we want to have this battery model exactly the same with the real battery. Yes, so your answer is correct. But I want to clarify that, you mentioned the current, you said you can see the current waveform is from small current to middle current and then to large current. And the current at magnitude is 1/5C. Those 1/5C, 1/3C, and 1/2C, 1C, 2C, 3C represents the magnitude of the current. Like small current, from small current to large current. Okay, so for 1C, in the battery, for 1C means we can fully charge this cell in 1 hour, which means for this battery, can you go back the specification of the battery? Yes, this. So you can check that this battery cell is 4,200 milliampere Ah. So to fully charge this capacitor, this capacity in 1 hour, we need to use 4.2 ampere. Okay, we use 4.2 ampere and charge 1 hour to get a fully charged battery cell. So 1C stands for 4.2 ampere. Okay, so you can see the magnitude of EHPPC current is from very small and to 1C, 2C, and 3C. The current is increasing. Yes. And so, by the way, this figure, it shows the OCV versus SOC. So these two experiments was separated. So firstly, we conduct this, we test this OCV, we measure the OCV waveform, and then after finish this, we discharge the battery from 100 to 50%. Could you go to next? Yes. And then when SOC is 50%, and then we perform this EHPPC experiment.